Hi everyone. Today we are going to discuss Module 5 of Advanced Manufacturing Technology ME306. So in this particular video, I will discuss basically two sections in Module 5. That is, one is high energy rate forming and stress waves. Okay, so we will move on to the topic. So this is the syllabus, and in this syllabus you can see in Module 5, it's the starting section actually says high velocity forming of metals. So definitely we need to know what is metal forming, and after that what is high velocity forming. And the questions usually which comes in university exams is like, what is the effect of high speed on the stress strain curves of steel, aluminum, copper? This is actually an important question, which will be asked maybe like for 6 marks, or it can be asked for 8 marks. And അവിടെ you need to do one thing. എന്താ ചെയ്യേണ്ടതെന്ന് പറഞ്ഞാൽ basically you need to draw a graph. So I will explain this particular portion, and after that what is high velocity forming, and what is actually stress waves, and there is actually a small equation, and you need to derive that equation. So that is all about this particular video. Okay, so we can move on to the topic. First one, so before going to high energy rate forming, since one of the term is forming, definitely you need to know what is actually a forming process. Forming is not like machining, because in the last videos or in the previous modules up to module 4, the processes what we have discussed were machining process. In machining process, basically what happens is that material will be removed, but in metal forming process we are not removing any material, rather we are actually shaping the material by means of some forces. So that is metal forming process, and we are actually not removing any material. Okay, so high energy rate forming. High energy rate forming compared to conventional forming process, what makes high energy rate forming process different is that here the load required for deformation is applied onto the material with high velocities, usually about 100 meter per second. That is high velocities. In conventional forming, the velocities what we are, if we are actually hammering a particular material, the velocity will be obviously less, right? So conventional forming process, the velocities are usually less than 5 meter per second. But in high velocity forming, we are giving a large amount of velocity, that is large amount of kinetic energy, and the velocity is normally about 100 meter per second. In this way, high energy rate forming processes actually deforms the material. So important features. This is also important because what are the characteristics of high energy rate forming process? You can expect this question also. So the energy of deformation delivered is at a much higher rate than conventional, because what happens is that velocity is high, right? So kinetic energy half mv square. So when velocity is high, the energy imparted to the material will be high. So corresponding deformation energies also will be high. And also large energy, this half mv square, that is this high high amount of kinetic energy is actually applied for a very short interval of time. That is another feature. And many difficult to deform materials, that is some materials are difficult to deform by conventional machining process, that materials can be deformed by this particular technique. And large parts also can be easily deformed. And the strain rate dependence of strength increases with increase. What is actually strain rate? Because the question, have shown in the previous slide, that is immediately after the introduction slide, we have discussed there will be a question like effect of strain rate on the stress strain relationships of three material. So in strain rate is important. Strain rate is nothing, strain divided by time. That is strain divided by time. Strain and what is strain? Strain is actually change in length divided by the original length. That is amount of deformation happening in a material. That is strain. And strain divided by time means, for example, if a particular material deforms, say by 20 percentage, and 20 percentage deformation is imparted to the material in 10 seconds, and the same amount of deformation is imparted to the material in 60 seconds. So strain rate will be more for which condition? 20 percentage and 10 seconds, right? Because 20 percentage deformation is given to the material in a small amount of time or short interval of time. That is actually strain rate. So in high velocity rate forming, strain rate dependence of strength, that is the material strength will be affected depending on the strain rate. For example, if I am just deforming aluminum with a particular strain rate, for example 10%, as pointed out in the earlier example, 20 percentage of strain is imparted to aluminum in 10 seconds, and again the experiment is repeated by imparting 20 percentage of strain to aluminum in 60 seconds. In both cases, strength of the aluminum will be different. That is the important thing. And along with that, as temperature increases, when we do this particular high velocity forming operations at high temperatures, because we can do high velocity forming operations at say 1000 degrees Celsius. I can do it at room temperature, or directly I can use some high temperatures, maybe like 1500. So as temperature increases, also strength increases. So here the important point to note here that the yield stress and flow stress at lower plastic strains are more dependent on strain rate. See, yield stress and flow stress at lower plastic strains. Small amount of strains. Lower plastic strains means small amount of strain are more dependent on strain rate than tensile strength. Strain rate dependency. So for small amount of plastic strains, the amount of strain rate given to the material is important. And yield stress is, you all know that yield stress is the stress immediately up to the point where yielding happens, that is up to the immediately after elastic limit, right? And flow stress is the stress after elastic limit, or the after the yield point and up to the ultimate point, that is flow stress. So these are the important features of high energy rate forming process. Okay, well, I'm not going to discuss what is high energy rate forming, because definitely in module 5 you have to study three high energy rate forming process like explosive forming, but I am not covering those topics in this particular video. Here I am explaining the essence of high energy rate forming process, especially the stress waves and the connection with connection of strain rate. Okay, and the effects of the previous slide says about the characteristics, and this one says about the effect of high strain rates during forming. High strain rates, when we give high strain rates during forming process, what happens? Here you can see flow stress increases with strain rates. Temperature of work increases, because as strain rate increases means we are actually giving a small amount of, or we are giving a particular amount of strain in a small interval of time, because high strain rate means time duration will be less, right? So temperature of work increases due to adiabatic heating, because we are not giving any time for the workpiece to dissipate the heat. So almost heating happens at constant temperature. That is temperature of the work increases. എങ്ങനെയാണ് temperature build ചെയ്യുന്നത്? Kinetic energy of the workpiece is dissipated as heat, right? And as I said earlier, many difficult to form materials can be machined. No necking won't happen. That is an advantage. No spring back effect. What is actually spring back effect? Spring back means in some depending upon the elastic modulus. That is elastic modulus, within the elastic modulus is basically stress divided by strain. So that is actually specifying the amount of elasticity of a material, right? So depending upon the elastic modulus, many material after deformation try to recover back. So there will be always a small amount of what to say, recovery after deformation. For example, if I am just compressing a particular material from 10 mm height to 5 mm height, depending upon the elastic modulus, if I am just checking the final height after compression, uh, definitely I am expecting 5 mm, right? So maybe it will be like 5.1 or 5.2 mm, because when the load is released, the material tries to recover back. That is zero point 0.1 or 0.2 mm. That is called spring back. So since here we are actually applying large amount of energy in a short duration of time, spring back effect is not there. No wrinkling. Wrinkling is actually one of the defects occurring in metal forming process. Okay, no wrinkling effect. And after that, the products which come out of this particular high velocity forming processes has good strength and good mechanical properties. Okay, so next one. So ഈ ഒരു ഇത്രയും ഫിഗേഴ്സ് കണ്ട് പെട്ടെന്ന് പാനിക് ആവേണ്ട. I will explain each and every figure. First one, because ഈ ഒരു പാർട്ട് അറിഞ്ഞ് this particular part അത് is needed. നിങ്ങൾക്കിത് ആക്ച്വലി no need to study all these figures because from exam point of view, definitely the question will be stress strain curve or the dependencies of strain rate on three different materials. So in that case, no need to draw all these figures. I will explain what is the essence of this particular slide, and after that I will go to what is required. Okay, so here you can see stress versus strain. It is actually a stress strain curve, and it is actually showing two materials, ductile and brittle. So you need to understand what is exactly stress strain curve for a brittle material and for a ductile material. Here you can see for brittle material, immediately after yield point, it breaks. There is no plastic regime, because plastic regime means initially stress strain curve there will be a straight line. After that, if the after this particular point, this is yield point. After this particular point, if the based on the loading, if the curve goes like this, you can say that is ductile. But in brittle materials there is no plastic regime, but in ductile material here you can see there is a plastic regime. So that is the difference between ductile and brittle, just for your understanding. And here you can see from the stress strain curve, definitely you need to know what is resilience and what is toughness. It will be usually asked in gate exams, interviews also. So resilience is the amount of energy absorbed up to the yield point. That is the area under the stress strain graph under the yield point. That is this particular area is called resilience. And whereas toughness is the amount of energy absorbed in a material up to the failure point. So toughness and resilience are different. So you need to know both. Toughness is the area under the stress strain curve up to the fracture point, and here resilience is the area under stress strain curve up to the elastic point. And here you can see this one is a tougher material because here the area is more. But this particular stress strain curve, here you can see the area is less. That is actually it's a stronger material because it can actually absorb energy uh, up to the yield point. That is actually good. But after that, this particular portion is less. So entire area is less. So the material is stronger because it exhibits a higher yield strength, but it is not tougher because over a long duration it will break. Tougher material can absorb shock or impact for a longer period. So that is basically stronger material and tougher material. So that was the main motivation why I put all these three figures, just for your understanding. The difference between ductile and brittle material, what is resilience and toughness. And the next two figures, this one and this one, it is actually required, because when a question comes like what is the effect of strain rate on the stress strain curves of aluminum or steel or copper, any three materials, because three materials in module 5 it specified that three materials, aluminum, steel and copper. So definitely you need to know what is stress strain curve of each. Here you can see stress strain curve of mild steel. This is normal stress strain curve of mild steel. Usually when we do a tensile test, the stress strain curve of mild steel will be looking like this. See, first there will be an elastic regime, and it will reach a yield point. Stress strain curve of steel has two yield points, that is upper yield point, that is it is denoted by YU, and after that it will come to a lower yield point, and after that plastic deformation starts, and it will reach to a particular value where U is denoted by ultimate strength. After that it fractures. This is stress strain curve of mild steel. Whereas stress strain curve of aluminum, here you can see initially there is an elastic limit, and it will reach as a particular point called yield point. After that this one is yield point, and after that again it will reach as a maximum point, that is ultimate point, and fractures. So here you can see unlike steel, there is no yield point, separate yield points for aluminum. So you need to understand what is stress strain curve of mild steel and aluminum before you need to explain what is exactly the effect of strain rate on these materials. Okay, so this is actually the question. The previous slide is just for your understanding, and the coming this slide and the coming two slides actually explain what you need to write in exams when a question comes on effect of high speeds on the stress strain relationships of steel, or altogether effect of high speed on the stress strain relationships of steel, aluminum and copper. So in that case you need to draw separate figures for each material. Okay, first you can see this one is a stress strain curve of steel, and here you can see the experiment was done at two different strain rate. One is 1 by 100, that is 1 by 1000, sorry, 0.001 second raised to minus 1, and 500 second raised to minus 1. So here which one is the higher strain rate? Obviously 500 second raised to minus 1, right? So here you can see for 500 second raised to minus 1, this was the curve, you can see, right? And for 10 raised to minus 4, this is the curve, this one, 10 raised to minus 4. And so as strain rate is increased, yield stress increases considerably. Here you can see as strain rate is increased, yield stress increases considerably means this one is 500, right? This one is the curve 500, right? This one. So here the yield stress, you can see this particular area, this particular area, this one, this particular point. Here you can see the yield stress increases for 500 second raised to minus 1. But yielding starts at a relatively lower value of strain. That means yielding, here yielding starts at a relatively lower value. That means, see, this is the value where actually yielding started, right? Uh, sorry, it's actually not like that. Oh, it's my mistake. It is not the yield point. Sorry, this one is the yield point, right? This is a yield point. This one is actually, this one is the yield point, and this one is the ultimate point, right? So here you can see at 500 second raised to minus 1, yield point is more compared to 10 raised to minus 4. So this one is the yield stress, this one. And yielding started at a relatively lower value of strain means here you can see for 500 second raised to -1 as strain rate increases, that is higher strain rate, yielding starts at a lower value, maybe like in between 0 to 8 as 15, maybe like I can give 8. So but when the experiment was repeated at 10 raised to -4 second raised to -1, obviously yield strength was low. See, you can see yield strength is low, right? And after that, then again, but yielding starts at higher values, right? Yielding starts at higher values. Yield strength is this one, but yielding starts at higher values, this one. So that is actually the effect. So you need to write these particular points. Yielding starts at higher values. Yield strength is high and yielding starts at lower values. This is the effect of high speed on the stress strain relationships of what? Steel. Then moving on to the next material, effect of high speed on the stress strain relationships of copper. Here you can see, here also see two different strain rate. As mentioned in the earlier slide, one is 1 by 1000, 0.001 second raised to -1, which one is a lower strain rate, and the second one is 500 second raised to -1, which is a higher strain rate. And here you can see, as strain rate increases, what happens? As mentioned in the earlier slide, yield stress is high. That is, yield stress increases considerably. That is, you can see for both this material, this one is lower strain rate and this one is higher strain rate. And here you can see yield strength is more. But yielding starts at relatively higher values of strain. Yielding starts at relatively higher values. Here, yielding for copper, yielding starts at relatively higher values, even though here we cannot exactly differentiate between two yield strength, but here you can see that yielding actually starts at relatively higher values, and increase in the yield stress is marginal. That is the major thing. Okay, in the previous slide, what you have seen, yielding starts at relatively lower values of strain. Here you can see yielding starts at relatively higher values of strain. Okay, for copper. And the next thing is aluminum. Aluminum also the same. Here they have done the experiment at 10 raised to -3 and 1300 instead of 500, because it is also a higher strain rate, right? Here considerable increase in the yield strength as the strain rate is increased. That is, this one is 1300 per second is the experiment which is done at higher strain rate. Here you can see yield strength is more, right? And for lower strain rate, 10 raised to -3, this curve, the yield strength is less. So these are the effects. So you need to mention you need to draw all these three figures and along with that explanation. Then only you will get the concerned marks. Okay. And then next topic is effect of strain rate. So usually it will be asked like for two or 3 marks. So effect of strain rate, what happens when the strain rate is increased? Definitely high deformation velocities develops stress waves which moves at high velocity. Here you can see stress waves. That is one of the important topic we are actually going to deal with in the coming slides. So stress waves is important. So when we apply deformation at high velocities inside the material, stress waves will be developed. Just like you can imagine when we throw a stone in water, definitely you can see waves, right? Similarly, in solids, stress waves will be developed. Stress waves will be developed and which moves at high velocities within the material. And velocity of stress wave is often close to the velocity of sound. So here you can see that this velocity of stress waves. So when we apply a large amount of energy to a material for a short period of time, or in a short interval of time, what happens is that immediately stress waves generated. What is actually stress waves? In a way, we can visualize materials are composed of atoms, right? So when we apply a large amount of force in a material, these particles will move or try to break from its atomic bonding. That is actually visualized as stress waves. So velocities of stress waves is often close to the velocity of sound. So just imagine how fast these stress waves will be moving through the solid. So moving dislocations. Basically, dislocations are nothing but group of atoms. So for a particular material to deform, the group of atoms should move. That is actually moving dislocations. Moving dislocations during plastic deformation experience a damping force due to this high stress waves. And this force is proportional to the dislocation velocity. And at high plastic strain rate, dislocations may be required to move so quickly that dislocations damping forces determine flow stresses. Nothing, as plastic strain rate increases, dislocation movement increases. Dislocations velocity increases. Thereby, materials deformation increases. That is the effect of strain rate. So you need to write all these points. So maybe like you will get 3 or 4 more questions from this particular section. And this one is important, elastic stress waves. And here I have already mentioned, when we apply a large amount of deformation for a short interval of time, stress waves will be developed. And the next question is, what are elastic stress waves and what are its classifications? What is elastic stress wave and what is its classification? So as I mentioned earlier, when a structure is subjected to a rapidly changing load, which is caused by impact or explosion, the part which is close to the point of application of the load can be highly stressed, right? And while a more distant area is still unaware of any loading, because where we are actually applying the load, there the deformation will be more, or at that particular point it will experience a large amount of force. And away from that particular point, the material which experience this amount of the amount of force experienced by the material will be less. So loading has occurred is carried from the point of application to the part of the other part of the structures by stress waves. That is stress wave. And in high energy rate forming, stresses propagate as waves, as I mentioned earlier. Time required for the stress to propagate becomes comparable to the rate at which stress is changing. അത് മനസ്സിലായോ? Time required for the stress to propagate becomes comparable to the rate at which stress. When we apply stress onto a material at different rate, as we mentioned earlier, strain rates. So as strain rate is different, um, the time required for the stress to propagate also will be different. So basically, determining the propagation characteristics of stress wave is really important. That is why you need to derive an equation determining the propagation characteristics of stress waves. And waves traveling through a solid obeys Hooke's law are called, which obeys Hooke's law are called elastic waves, because waves can be classified into different types, but we are actually dealing with elastic waves and waves which obeys Hooke's law. Hooke's law എന്താണ്? Within elastic limits, stress is directly proportional to strain. That is, immediately when we release the load, the material will come back to its original position. So similarly, when the effect of wave is not there, the material will regain, or the particles inside the material will come back to its original position. That is, the waves which obeys Hooke's laws are called elastic wave. Okay, and elastic waves. As I mentioned, this you can just take a snap of this particular slide and just read it out. Okay. And yeah, types of elastic body waves. There are two different types. This is actually an important question. One question you can expect from this particular topic is, what are the different types of elastic body waves? Explain, maybe like for 6 marks. Or explain the following waves. P wave and S wave. So if you know that only, you can write. Okay. So longitudinal. So basically types of elastic body waves. All these comes under this particular classification. So first type of classification is of elastic body wave is longitudinal wave. Here you can see longitudinal wave. Longitudinal wave is also called P wave. P stands for primary or pressure or push-pull. Anything. So P waves, longitudinal waves are also called P waves and also called compressional waves. Why? Why they are called longitudinal waves or compressional waves? Here you can see undisturbed. Undisturbed means before applying the load onto a material, atoms will be arranged like this. And suppose due to the application of load, a longitudinal wave develops inside a material. Then what happens is that this particular group of atoms will come together. They will experience a compressive force. That is in the direction of wave propagation. That is, P wave is transmitted by the particle movement back and forth along the direction of the wave such that the particles experience a compressive force. That are called P waves for primary waves or pressure or push-pull waves. Push-pull means it is actually pushing this particular group of atoms and this particular row of atom is actually pulled away. So this is actually called P waves or the longitudinal waves. And the second type of wave is transverse wave. Transverse, from the name itself, transverse, it is actually perpendicular, right? And transverse waves are also called S waves. S stands for secondary or shear. So why transverse wave? Transverse waves because particle motions are transverse. You can see here the particle motion. Here this is the undisturbed atoms, and when a load applied onto the material create a S wave. Here you can see the particle motion is actually perpendicular, right? That is actually shearing happens. It involves shearing of the material. This is called S waves. So this will be usually asked for 4 or 6 marks and you need to explain the two different types, P waves and S waves. Okay. And the last topic, last topic is longitudinal wave equation. You need to derive a longitudinal wave equation in an infinitely long rod. Here what I will explain the essence. You need to consider a infinitely long elastic rod. And what this particular equation, finally we will write or we will derive an equation, and that particular equation says the propagation of waves is based on this particular velocity. That is, how to find out the velocity of the waves propagating in a solid. That is the equation. And you need to know this particular point or this assumption. It is an infinitely long rod. Okay, so we can move on to the topic. So this is the bar. We are actually considering a long bar, and in this bar we are actually taking a small section which is having a length dx. And when a pressure or force is applied onto the particular end, only to this particular end, to the one end, definitely what happens? Stresses will develop onto the material. And this one is an enlarged view of this particular dx. Here you can see, as stress waves propagate, this portion will experience a stress sigma. Sigma is nothing, load divided by cross-sectional area. Sigma equal to P by A. And this particular part will experience a stress which is equal to sigma plus dou sigma by dou x into dx. This is differential equation. That is, the variation of stress along a length dx is given by sigma plus dou sigma by dou x into dx. This is the actually what we are actually considering here. We will take a small strip and we will analyze that and we will integrate it. That is the essence. Okay. And here you can see this is Like sigma, you need to know other parameters. Strain also. Strain, how you will calculate strain. Strain is basically change in length divided by the original length. Here you can see displacement is the initial displacement in the axial direction is u. U of x and t means it is based on length and time. And normal stress is given by sigma. We have seen face A of the element is displaced by a distance u. That means face A is displaced by a distance u and face B is displaced by a distance u plus dou u by dou x into dx. You got that? Here I will show you this particular figure. This is A and this is B, and here you can see this particular A is displaced by this particular distance, which is called u. This particular distance u, and B is displaced by u plus dou u by dou x into dx. That is this one, u plus dou u by dou x into dx, and this one is u. Okay, and so coming on back to the previous point. So here you can have seen the face A of the element is displaced by distance u, and face B of the element is displaced by u plus dou u by dou x into dx. So finally what happens? Strain in x direction, epsilon x, right? Epsilon x is given by what is exactly the difference in strain, that is u plus dou u by dou x, u plus dou u by dou x into dx minus what is u, right, divided by the original length. What is the original length? This one, dx. So I am just dividing this by dx. So what happened? U and u will get cancelled out, and finally dx and dx will get cancelled out. Finally we will end up in dou u by dou x. So epsilon x equal to dou u by dou x. And similarly you need to write this dou u by dou x in terms of sigma and E. So all we know that sigma x is related to epsilon x through this particular equation, right, where E is the elastic modulus. And substituting the value of epsilon x, this one, value of epsilon x, dou u by dou x in this particular equation, we will get sigma x equal to E into dou u by dou x. This is one of the important equation because you need to know this particular equation so that we will substitute this particular equation in the later part. So sigma x equal to E into dou u by dou x. Next thing is that this one I have already explained, right? This is a part, and this was actually displaced to this particular dotted line is the next part, that is this after displacement of u, and whereas B displaced to this particular area, that is this particular portion dotted line, and the displacement was u plus dou u by dou x into dx. And also in A the stress was sigma x, and in B it was sigma x plus dou sigma x by dou x into dx. Okay, then so if we take phase A and phase B, that is this particular phase and this particular phase, what are the parameters? In phase A, the displacement was, phase A was displaced by u, whereas phase B was displaced by u plus dou u by dou x into dx. Similarly, stress at phase A was sigma x, whereas stress at phase B is sigma x plus dou sigma x by dx. And next thing is we need to find out the force. If we know stress, definitely by multiplying stress with stress is force by area. So to find out the force, stress has to be multiplied by cross section area. So sigma x into A gives force at phase A. Similarly, sigma x plus dou sigma by dou x into dx into A gives force acting on phase B. And acceleration. Acceleration is nothing but change in velocity divided by time. Change in velocity, dose dose change in velocity divided by time will give acceleration. And definitely velocity is change in displacement by time. Here displacement is u, right? So u divided by t, again it is differentiated 2 times. That's why dou square u by dou t square is the acceleration at which phase? Phase A. That is acceleration at phase A. Similarly, acceleration at phase B is given by dou square u by dou t square plus dou square dou by dou x into dx by dou t square. And we will neglect this particular term, this one, only this particular term, this one. Higher order differential term is neglected, and average acceleration of the element dx is taken by average of dou square u by dou t square and this one, this particular thing. So average acceleration will be dou square u by dou t square. Okay, and then after that what happens? Average acceleration, we got average acceleration dou square u by dou t square. And the next thing is we need to find out the net force, because it is the net force by you need to find out based on the Newton's second law, F equal to ma. Here we have found out acceleration. This one is acceleration. Acceleration was dou square u by dou t square, right? Then net force is given by this particular expression, this one. Net force equal to net force in A, this one, sigma x plus dou sigma by x by d dou x into dx into A minus sigma x into A. This is what we have seen in the early. See, here you can see force acting on the phase A and B. Actually, what they have taken is this force minus this force. So we will end up with F equal to dou sigma by x by dou x into dx into A. And then if we have found out f, right, which is dou sigma x, dou sigma x by dou x into dx dA, dx not dA, dx into A. And only remaining thing you need to find out is m. M is given by this one, mass. This is the mass. Sorry, not this one. This one is the mass. Mass is density is equal to mass by volume. Mass is equal to volume into density. Here volume is area into dx into rho. So rho a dx, it can be rewritten as rho a dx, which gives mass. So rho a dx is mass. This one is acceleration, and this one is force, and this one is acceleration. So putting all these things, we will get dou sigma f is equal to ma. This one is force, this one is mass, and this one is acceleration. And simplifying this particular equation, we will get this particular one. And you know that sigma x equal to E into dou u by dou x. So here what they have done, they have changed this particular thing into, they have taken sigma x and rewritten into in terms of E. That is dou sigma x by dou x can be written as, since sigma x equal to E into dou u by dou x, this particular thing was substituted here for sigma x. Dou by dou x of E into dou u by dou x. What happens then? E can be taken out and dou square u by dou x square. This one is dou square u by dou x square, which is equal to, so again it can be equated to this one, equal to rho into dou square u by dou t square. Again rewriting, we will get dou square u by dou t square equal to E by rho into dou square u by dou x square. So this is the final equation, this one. So dou square u by dou t square equal to E by rho into dou square u by dou x square. And here we have mentioned like stress waves travel with the velocities of sound. So definitely if we can relate E by rho with velocity of sound, it will be good. So E by rho is related to velocity of sound using this expression. C equal to root of E by rho. So substituting that, we will get dou square u by dou t square equal to C square into dou square u by dou x square. And this is called elastic longitudinal wave equation for a rod of infinite length. So when a question comes for 10 marks, usually it will be asked for 10 marks, you need to derive this equation. Okay. So please watch the video and നിങ്ങളുടെ ഫ്രണ്ട്സ് ഉണ്ടെങ്കിൽ just share ചെയ്ത് കൊടുക്കുക. Okay. So that's all for today. Thank you.